So now let's take a look at the scheduler in the Linux kernel. So throughout this course, I'll be showing you different parts of the Linux kernel at different points of time. So since it's the first time we're looking at it, let me actually do sort of an introduction to the Linux kernel. So the Linux kernel is one of the most widely run pieces of software in the world. The Linux kernel started off as a project back in the 90s when Linus Torvalds, who was a student at the time, he wanted to write a new operating system basically for fun, right? So what he did was he wrote this small piece of code which later turned into the Linux operating system, and then he put it out for comments in the sort of mailing lists of the world at that point of time. And a lot of people really liked how simple the Linux operating system was, and how it was easy to modify different things in the Linux operating system. So it really it caught on. More and more people started using the Linux kernel, and over the years, the Linux operating system has become sort of the de facto standard for open source. So in many of these sort of computer science startups and companies in the world, you would see them running Linux. And it's open source. All the code is available, so you can modify it as you want. And it's also a very educational piece of software, right? An operating system is something that has to run efficiently. You can't, if you wrote a really slow running operating system, most people wouldn't use it. So it's also a very good exercise in how do you write a really high performance piece of software, right? And because it's open source, and most of the code, or some of the code, has very good documentation, and people are very responsive on mailing lists, it's a very educational piece of software. And I think most operating system courses will at least give you some introduction to the Linux kernel, and I highly encourage students to sort of get more familiar with the Linux kernel as they do systems related projects. So here, if we look at the sort of terminal, what I've downloaded is the latest stable version of the Linux kernel. As of today, that's Linux version 4.20.6. So we just downloaded the Linux kernel, and it has lots and lots of different files, right? So this is an operating system which today has sort of the unique property that if you took a really old computer, let's say from the 90s, Linux would run on that. If you took a supercomputer, Linux would run on that. So it's a very versatile piece of software, and as you'd imagine, to actually do this, there's a lot of code in there, right? So one of the first things that you want to look at is you want to notice there's lots of different folders. The stuff that we'll be interested in will be very isolated. We'll be looking at the scheduler, the file system, and so on. So you don't have to worry about all the device drivers and all of that. So we'll be looking at specific files. Now one thing I do want to point out is that Linux kernel actually has reasonably good documentation for a lot of different things that it's doing. For example, today what we're interested in is looking at the scheduler that is used in the Linux kernel, and this is called the completely fair scheduler. And so the Linux kernel ships along with documentation about the scheduler. So that's what we're going to look at first, right? So so here the path I'm looking at is so documentation folder contains text files which are documentation about different aspects of the Linux kernel. So we're going to look at the scheduler, and the thing we're looking at is the design of CFS, or the completely fair scheduler, right? So if you're going to look at it, it's fairly nice. The people who wrote CFS went to some effort to give nice overview of what they were doing, right? So so this was this was merged back in Linux 2.6.23, right? So to give you a little bit context of what merged means, so the way development happens in the Linux kernel is there's a current master branch which contains the latest code, and what you do is you submit patches. A patch is basically a diff file of the current state and the code that you wrote, the difference between the current state and what you wrote. So you submit a patch to the Linux kernel, and then the current developers and maintainers of the Linux kernel will take a look at it, and they'll be this stuff has to change, this design doesn't work, and so on and so forth. And then you will redo the patch, you will make those changes, and then you submit a different version of the same patch. At some later point of time, everybody will be like, yes, this patch looks good, and then we're going to merge it into the Linux kernel. And so that's really what merged means. Like, it's now become part of the code base of the Linux kernel. And over the years, hundreds and hundreds of people have contributed to the Linux kernel, right? So it's no longer, like, it started off as a project of Linus Torvalds, but now it's really like the result of effort of many, many people. And the nice thing about it is, like, you can actually contribute to the Linux kernel too, and I highly encourage students to do it at some point of time. So anyway, if you look at the Linux kernel version, now we're at 4.20, and then this was merged back in 2.6, right? So fairly back, I think there was around 2007 is when this scheduler was like merged into the Linux kernel. So it replaced the previous scheduler, and the high level overview is like basically, they say it in a very simple way, it's very nice. So CFS models an ideal, precise multitasking CPU on real hardware. So what does this mean, right? So and if you read the rest of the overview document, they actually at a very high level they explain like what is going on reasonably well. It's very nice. So I highly encourage you to sort of like as you go through this course, whatever it is that we're talking about, go to the Linux kernel, look at documentation, see what they've written about that particular thing. So that's documentation, and let me actually like move over to the iPad, and then I will sort of sketch out like how this algorithm works, and then we'll go look at like some of the code that's in the Linux kernel, right? So overall we have the completely fair scheduler, and so when you're looking at the iPad. So in the completely fair scheduler, the idea is that at each point of time, you want to run the processor, run the process that has run the least amount of time compared to how much it should have run. So one way to think about it is that let's say there's a heap, and for like students who don't understand what a heap is, basically it's some data structure, which I'm going to denote in this way. And what it allows you to do is it allows you to keep the elements in it sorted by some metric. And whatever is at the top of the heap is the thing that you want to use next, right? So for example, let's say the heap contains numbers and you want to sort them based on like how big the number is, right? So so you can imagine like inserting 3, 5, and 8 in the heap. Let's insert actually 10, 3, 5, and 8, so that there's some sorting that's going on. And at each point, so after you insert 10, the top of the heap will be 10. After you insert 10 and 3, the top of the heap will be 3. After you insert 10, 3, and 5, the top of the heap will be 3. And when you insert 8, the top of the heap still remains 3. You can pop 3 from the heap, and then the next thing it will return to you as top is 5. So the heap is simply a data structure that allows you to basically keep your elements sorted and then pop the top element in order of 1. So what that basically means is in a very, very cheap way, like it doesn't cost a lot to get the top of the heap and to sort of like figure out what is the least sorted element according to some metric, right? Anyway, so long story short, CFS uses a heap, and what it actually puts into the heap is what it calls the virtual runtime. Okay, so let's abbreviate that as VR. Okay, so so what you do is you have a bunch of processes, and then every process has this metric, which is the virtual runtime. And what you do is you insert all of that into a heap, and then like whatever process has the least virtual runtime, you run that process. So it's a very, very, at least at a high level, very simple process, right? You put all your processes into a heap. You account for the virtual runtime of each process. Whatever process has the least virtual runtime, you run that process. So it's a very simple metric in that way, right? Of course, the real sort of like complexity is like what is virtual runtime and how do you calculate it and so on, right? So this part is sort of like complicated, right? So virtual runtime is basically it captures like execution time, like how much the process should have run, and it also captures like ideal execution time. So broadly, what virtual runtime is if there's a process and there's no other process in the system, like it would have run a certain amount of time, right? With the arrival of other processes, it would have run a different amount of time. For example, if you have a processor, and then if you have a single process, that will of course run 100% of the time, right? There's nothing else competing. But if there's two processes, P1 and P2, now each will run 50% of the time. Now that's really the fair case, right? Like that's really what we want to happen, right? Now, one way to think about virtual runtime is it measures like how much you have actually run versus like how much you're supposed to run. So what do I mean by that? So this is not actually how virtual runtime works, but it gives you like a good high-level idea, right? Let's say, for example, we somehow kept track of like how the percentage like this was running. So, for example, let's say in every 100 nanosecond window, this should have run for 50 nanoseconds, and then this should have run for 50 nanoseconds. Fair, right? And then we keep track of like how much it actually ran. So let's say this ran for 23 nanoseconds, whereas this ran for like 77 nanoseconds, right? Now, the way virtual runtime is calculated is the virtual runtime of process P1 will be lower than the virtual runtime of process P2. So if you look at our heap, and then process P1 will be at the top of the heap, so we will pop process P1 and then we will execute P1, and after we execute it, the runtime will change, because like let's say we now execute for another 20 nanoseconds. Right? So we have now executed more, and so again, like still process P1 might be the top of the heap. We don't know that yet, but as we execute, we change the virtual runtime of each processes, and because of that, the top of the heap may change, and then whatever is the top of the heap, we pop and then we run it. So the actual calculations of virtual runtime turn out to be a little bit more complicated, because you have to take into account stuff like the priority of the process, how much it was supposed to run, how much it actually ran, how many different processes are trying to run on the same processor, and so on. So the actual code ends up being a little bit complex, but at a high level, what the code is trying to do is just this, right? Track how much the process has used, how much it is supposed to use, and whichever process has used the least, you run that process next. So that's really the high level overview of how the completely fair scheduler works. Now there's a bunch of like details in the completely fair scheduler. So it has different classes of processes. So for example, there is the other category, and this is really everything, like all your shell scripts, your development, all of that runs in sort of like other. There is also sort of like real time. Sorry, not real time. That's a different thing. There is also batch. So batch is meant for process where they are computation bound. So for example, let's say you are calculating the first million digits of pi, right? So that's entirely computation bound, and you don't want to context switch that process too much, right? You want to let it run as much as possible. So those processes will be tagged as batch, and the point is to not interrupt them too much, right? Whereas your other is for all your normal regular processes, and there you want it to be interactive, like when you type something on your keyboard, you want it to appear on screen. So for that you use other. There's also idle, and idle is really meant for the case where it's all for your background processes, right? So we don't know about this stuff yet, but let's say there's a bunch of background work that needs to happen in the operating system, right? You want to flush dirty data to storage and stuff like that, right? So you want to run this stuff only when no user is actually using that processor. So if any user is actually running a batch process or an other process, you want to give priority to that. But if none of them are running, there's a bunch of cleanup the kernel needs to do, and you want to run idle at that point of time, right? So these are the different classes that are allowed by CFS, and within each class you can have different rankings. For example, within other you can have like 0 to 100. So a process with ranking 1 in other will have higher priority than a process with ranking 100 inside other. So within each class there may be multiple processes with multiple priorities. So CFS allows all this complexity, but at the end of the day, all of these things will boil down into virtual runtime, right? And the algorithm remains the same. Pick the process with the least virtual runtime, run that process. So CFS is very nice in the way that like all this other complexity that prior algorithms had, it was able to reduce them down into like the virtual runtime concept, right? And as you design systems, this is a very desirable property to have. Like you want to design a general system which allows you to implement a bunch of other things, and in which all the other complexity of a system can be boiled down into simple constructs. So you can take anyone, you can explain the high level goal of CFS and virtual runtime very quickly, but it actually internally it does take care of like like batch processes and interactive processes and all of that. So that makes it a very nice design. At a high level, that's really like how CFS works. So let's briefly look at the code behind CFS. I'm not going to go through the entire code, not like how we did it with the XV6, but I'm going to give you enough so that like if you want to go look at CFS on your own, you will at least know where to start, right? So let's take a look at the code. All right, so we are going to go into the kernel folder, and then inside the kernel folder, inside the kernel folder, there is of course going to be like a whole bunch of files. We are once again going into the scheduler folder, and inside the scheduler folder we have a different, we have a bunch of files, and what we're going to look at is going to be fare.c, which really implements completely fare scheduling. And one of the nice things about this file is that like you can see the history of people who have done improvements, right? So Ingo Molnar did the original CFS algorithm, and then Mike Galbraith and a bunch of others actually did a bunch of like optimizations over the years, right? So this file that you're looking at is really the sum of all their efforts, right? So what we're going to look at is like it's a huge file, right? It's a very complex piece of code. It's 10,000 lines, which is why we're not covering it entirely in class. But we are going to look at like some of the stuff, right? So this basically is the function which updates the current task's runtime statistics. So what that means is CFS has picked some process to run. As it runs, we have to update virtual runtime so that the next time we pick, it's accurate, right? So we can see that what it's doing is like it's getting the current clock time, and then it's calculating the difference between the current clock time and when the process started, right? This is basically what you'd expect to find. The process started running, and now we are at time 20. It started at time 10, so we're calculating the difference between these two to figure out how much time the process has run. So fairly reasonable code. And so then what we're looking at is like we want to update the virtual runtime of the process, but we want to update it in a way such that it takes into account all the other processes that are trying to run on this process. So if we just took the difference between start and now, that would be like that wouldn't take into account the fact that there is this ideal time that is supposed to have run, right? So let's go look at like delta fare, right? Yes. So which calls another function. At a high level, right, like this is what it is doing. So it is calculating the difference. In our example, 20 and 10. 10 is what the value of delta exec, and then each process has a separate weight associated with it, right? So weight is like different word for priority in this instance, right? So a process which is important will have like very high priority. So for example, let's say a process is like executing with the highest priority in the system, that will have weight that is the maximum value. So when you do this division, that will be 1, and so like it will be as if the process has run for the entire amount of delta exec. So in our example, 10 milliseconds or nanoseconds or whatever. But if it's a process which is like low priority, then the weight will be lower, and so it will account for lower amount of time. Anyway, so this is sort of like how all of this is calculated, and like there's a bunch of like interesting stuff in there. But this is where you should start if you want to look at like completely fair scheduling. So I encourage you to go look at the code and like ask questions. Right. With that, we have taken a look at like both XV6 and the Linux kernel scheduler, and then we'll do a review of scheduling, and then we'll move on to memory management.